final lecture on LHC physics.
Okay, so this is the third lecture, and now we're going to go for searches beyond the standard model and look at a couple of examples and the kind of searches that are ongoing at present. Beyond the standard model, why? Again, Cornelis will discuss that as of tomorrow in some more detail, but here you see some of the elements which lead us to believe that we are we can look with the LHC for physics beyond the standard model. First of all, the standard model, are we unhappy with it? Basically, we're not terribly unhappy with it because it works to like order per mil precision or so in particular measurements we can make. So we haven't seen actually a region where it is really breaking which we all agree upon that that's a region where things go wrong. But we know that the model itself doesn't actually explain a lot of things. It has a lot of parameters in it, 19 to be sort of exact if you count for it. And it doesn't explain particularly why, for example, so far we see 3 flavor families, maybe there are even more flavor families. What are the mass spectra which we are having in the hierarchies which we are seeing? And if you really want to take the standard model seriously up to very high scales, very high energies, like the Planck scale, you're going to have to do an enormous fine-tuning. Fine-tuning meaning you're going to have in the model mutual cancellations of possible divergences so that you get a stable situation. And I always compare this with a pencil. If you take a pencil and you put it on a stop, on a sharp point on the table, if you're very good, maybe you can keep it for a second or so when you release it, and then it will fall to one side or the other because something is not perfectly cancelling in the gravity around it. Well, to tell you this kind of fine-tuning you have here, you have to keep the pencil standing like that in the room for something like 10,000 years. So that's a very extreme fine-tuning which people feel very uncomfortable with. So these are all reasons why people think that there is possibly something behind the standard model. Also, if you look at the couplings, and you see how they evolve with energy. Of course, we measure only the beginning here of that in the experiments. They seem somehow to converge to a common point, so like a unification of the coupling constants if you want, but not exactly. They miss each other. So that looks almost like, well, there is nothing that forces nature to have only coming everything from one force at high energies and then developing into 3 forces. It looks like a missed opportunity that they come so close and still they miss. And typically with extensions of the standard model, for example like supersymmetry, which I will show a little bit in a moment, you can deviate, you can make changes in this way the coupling constants evolve with energy so that you get the bending so that in fact they can indeed meet in one point. Now that's more intuition than anything else, but it tells you that something could well be around the corner here. And for example, I mentioned supersymmetry. Another one which has been popular in the last 10-15 years or so is extra space dimensions. But there is a whole slew of possible ideas, models, theories of going beyond the standard model for explaining sometimes facets of what we see here, not necessarily everything, which could manifest itself, mainly driven that something should happen somewhere around the electric weak scale, probably in the TeV range. And therefore, of course, with the LHC, we're going to look for it. You see all kinds of names here, like little Higgs model, technicolor, hidden values, left-right symmetries, substructure of quarks and leptons. It's a whole zoo out there, and theorists badly need data to be guided and to erase some of these possibilities here. And that's what we're providing. So, new physics at high energies. Could it be new gauge bonds we are seeing? Say, family members of the Z and the W boson just much more heavy, like 1000 GeV or so, or higher, which had to do maybe with other symmetries, which we haven't actually seen yet, but which will become apparent as we go to higher energies. I mentioned supersymmetry. There could be resonances, which could happen there before. There could be a new kind of force, like a color force, but not quite the same, called technicolor, which would also lead to a number of particles in the hundreds of GeV range, which we would be seeing. Maybe there are extra dimensions, and I will say a little bit more on that, how that could manifest itself. This is just a cartoon how it could happen. For example, gravity moving away from the dimensions where we are living. If that were to happen, maybe, and probably you've heard about that at some level, maybe we could even make something like micro black holes at the LHC. And other models, such Little Higgs, Hidden Valley. As experimentalists, we have to be very, very open-minded indeed, because any of that could happen, or other things, maybe not even thought of. And of course, as I said, for theorists, it has been a pleasure to work the last 10, 15 years, pleasure on quotes, because there was no data actually to constrain what is happening at the high energies, what could be the next door behind the standard model here. Now there's a little bit of panic in town, because data are really coming now, and starting to clean up things. And I showed this on this picture. This is almost 10 years old. It's Hitoshi Maruyama, a theorist from Berkeley and also from the University of Tokyo right now, who made this at that time to give us a picture of an idea of what the zoo of possible new theories is. And maybe you don't see it too well from the back, but you have like Majorons, axions, supersymmetries somewhere in this particular corner here. Sterile neutrinos are here, hypercolor, composite Higgs, whatever. It's sort of all mapped here. And particularly, notice the regions not yet thought of, which are there. Also, when we were starting to complete the experiments, you know, we designed the experiments basically in the 90s, and we constructed them in the earlier part of the last decade, up to the end of the decade, in fact. So the experiments were quite fixed how they're going to look like and what they would be able to do. It became a sport of our theory friends to tell us what we would not be able to measure, because they thought of new signatures, which were of course not known in the 90s, but became particularly apparent in the second half of the last decade, and for example led us to real challenges, like for example slowly moving particles which are going to the detector, or particles which are changing charge, or things in the detector, all sorts of weird models. And as said, all that is possible because there was no data. That gave us a lot of headaches, because we had this detector being developed, and we have somehow, we would not want to admit to theorists we could not possibly measure that, so we had somehow to find ways of measuring that, and somehow even introduce some changes in the detector, which was already being constructed, just to catch these difficult guys here. So now it's our turn to strike back from the experiments, and on this nice plot which you see here, we start nicely to exclude regions with our data, even in, and I like this, even in space where they haven't even thought of. Actually, this was a slide made by a theorist based on some of our results which we have. You shouldn't take it too literally, but it shows that that is what data will be doing. And of course, hopefully one of these islands here will at the end remain and be true, or several of them, and we have to figure out what it is. One of the prime candidates for, you know, maybe it's of the order, I think perhaps 50% of my theory friends, which I hope is not too biased, are betting their money that probably what we're going to see is supersymmetry. Supersymmetry, that is low mass supersymmetry. So supersymmetry in the TeV range, not supersymmetry at the ranges of where strings are perhaps important. So what is supersymmetry? Supersymmetry is simple. Supersymmetry says that for each particle which we have in the standard model, we double that. So each one gets a brother. The only difference being that the spin of the corresponding particle here, so the U quark with the U quark partner here, differs by a half. And that's true for all the particles which we see here. So these are spin 1/2 particles, these are spin 0 particles. These are spin 1 particles, these are spin 1/2 particles. And it would also need the Higgs, in fact, to be there, so there will be a brother for the Higgs as well in there. Now, technically, these particles, particularly these ones, will mix in so-called gauginos and charginos, but that's sort of the picture. And they get names like they have quarks and leptons here, get squarks and sleptons here, for supersymmetric quarks and supersymmetric leptons, but that's too much of a mouthful, so they contracted that, and the both gets typically an eno on that. We have an Higgsino or a Photino or something like that as the partner. The thing we know about is that while they should have the same couplings in order to have these cancellations to work, which I will also show in a moment, they are certainly much more heavier than the ones we have here, because we haven't actually seen these yet. So they should be of the orders of 100 to hundreds, maybe of GeV, maybe TeV, if they exist in the low mass range. This is how we would produce them at the LHC. So at the LHC, we have what we call colored collisions, which mean colored objects collide. Quarks and gluons have color. And so preferably also we will produce colored objects in the superspace. So for example, this collision of whatever it is, two gluons or two quarks here can lead to two gluinos coming out, the partner of the gluon coming out here. Typically, these particles are expected to be very unstable and decay immediately. And in the decay, we believe that there is, in most cases of the models, this is not always true, but in the most current models, which are the most actually interesting ones also with respect to dark matter, that there is a quantum number, call it a supersymmetry number, which is conserved at each decay here. So that means if you have a supersymmetric particle here, you have a decay, there must at least be one supersymmetric particle coming out here, or an odd number of that. And that goes on, you have a cascade of decays, until you come and you decay into the lightest supersymmetric particle which we have here. Maybe that's the brother of the photon, for example, the photino. But that's it, they are a little mixed, so there's called the lightest neutralino, the lightest particle with no charge. And that, if indeed we have this conservation of supersymmetry number, technically called the RP conservation, then that particle cannot decay anymore because it cannot shake off its quantum number, and therefore is doomed to live forever. And that could be a particle several hundreds of GeV of mass, so in fact that could be a perfect candidate for dark matter. It's particularly in the realm of dark matter where it would be, and if we make calculations of the amount of dark matter we have in the universe, in fact we can calculate back a window where indeed we would be able, this particle to play that role. In fact we will produce two, because here we have a pair produced particles of supersymmetric particles, and there will be another one in the other chain as well. In fact, that's a very important characteristic for the search for supersymmetry, that there will be a particle, neutral, very, very weakly interacting, which will actually escape the detection. We will not see that particle, and that will lead to missing, for example, transverse momentum, or the momentum in the transverse plane of the totality of this event, which is one of the main characteristics. So, here are a few, just for the sake of completeness, here are a few of the virtues of supersymmetry, why it would be nice. For example, the reason why supersymmetry would help to cancel a lot of headaches we have if we normally release a Higgs round and we look at high masses. What happens that we see that there are divergences happening because these particles, because of their spin 1/2 difference, these loops cancel exactly against these loops, which would otherwise blow up the mass of the Higgs here. So that is what stabilizes this, what I was saying before. And there are another number of things. It, for example, can accommodate very easily a heavy top quark, and it has this dark matter candidate which I talked about. So it's still consistent with precision measured data and so forth. If we were to discover supersymmetry indeed in the next years, then this would be a real revolution in particle physics, I think. This is something on which people have been producing papers for the last 20 years, just by assuming that this is the last symmetry which they could use, the symmetry between fermions and bosons, and that would lead to all this phenomenology which we'll have here. We'll see if it is true. What's the situation today? So, this is a simulation, but it's how an event could look like in the detector. Lots of activity, jets for example, with high energy which come out because the gluinos we produce are expected to be rather massive, 500 GeV, maybe more. So they break open in jets, so there is a lot of energy in these jets, which you see in the detector. And you see an imbalance in the detector, and this imbalance, if you balance it with, this is just a 4 vector which balances whatever is here, goes that way. That is the net result of these two neutralinos which are going to escape. On the experimental side, just as a, in between brackets, this is, for that kind of measurement, one of the more important ingredients. And it's a very difficult one. It's measuring the missing transverse energy. So you look in the transverse plane You add up factorially everything what is around there, and you would see it should be 0, since the incidence beams, when they come in, they have a total transverse momentum of 0. You will always see it's not 0, it's non-zero. And that can be because of detector effects, which you see mostly here, or it could be due to new physics, which you would expect in these tails here. So this is just to see what the experimental challenge for that is, because it's a very difficult measurement. It's not as easy as measuring an electron or measuring a muon or even measuring a jet. Because whatever happens in your detector and what goes wrong, or whatever you miss to measure in your detector, is going to give you contributions to this tail here. So one of the exercises, and people told us before we started from experience at other colliders, that we wouldn't be able to use that kind of measurement for a few years before we cleaned it up. That was a Tevatron experience. Because that tail here is not new physics. That tail is effects which you get in. Maybe a cosmic ray that came at the same time as your collision, for example. That creates all missing transverse momentum in there. But in fact, it's one of the beauties of the experiments which we had, that in a few months already, both Atlas and CMS could have enough cleaning tools to make sure that with the simplest of collisions we understand the missing ET spectrum and we don't have this weird tails hanging out here. And the resolutions for measuring this missing ET seem to be very good indeed. So, then we can move ahead, and you see there is a whole like of plan or diagram one has for following SUSY. And this was last year. It was very simple, when we had like 7 or 8 classes or so to look at of different characteristics. Characteristics like it's an event with jets, at least 2, 3 big jets, 100 GeV, 150 GeV, and this missing transverse momentum of the order of 100, 200 GeV or so. Then another class is you have jets, but 1 lepton, 1 electron or a muon in there, because that's a different chain of decay, and it's also a different sensitivity to different models. Maybe 2 leptons, opposite sign or same sign, multi-leptons, and here maybe we don't have to use missing ET, we can have, because the reason why you were asking this missing ET is basically to suppress backgrounds. We have standard model processes which are plentiful around there, with cross-sections with orders of magnitude bigger than what we would expect here, and to clean that up, we must find stringent cuts here. Or others with photons and leptons. Right now, I think for this year's strategy, we have something like 36 boxes of different signatures which people are looking at, particularly using B quarks and stuff like that as well. And you have jets, you could also separate still if it's 2 jet, 3 jet, 4 jets. They all have a different sensitivity to different classes of models and different parameters of a similar model, of the same model. So, just to show how it is, how you do this work, you define your event selection criteria. Typically, you tune that on a Monte Carlo, and then you go to the data. Now we have 2 billion events triggered and stopped, and this is what you have to get over to look for that. In fact, we're a little more clever than that. We have already subcategorized these a bit in sort of like 10 categories, where there are jets, leptons or not, and then so you have to go maybe only over 200 million, but still a lot of events which you have to deal with. You go over all that. You use particular tricks and techniques, kinematic cuts, to optimize your signal over background. Then you predict these backgrounds in the signal region, typically using data itself, but outside of that region, and trying to extrapolate in what the background should look like. You determine efficiencies and systematics for your signal and for these backgrounds in here. And then you open the box in principle and you look at that. Do you see more than your background, or don't you? Or do you see exactly the same? If you see less than your background, you have actually a problem. You have to understand something. And so far, up to the analysis which have been released to date, which is about up to half of the full statistics being used in the last sample of data, so 1, 2 reverse femto bonds. So far, no excess of any kind has been found. And you see how much, with even 1 year of operation, you see how much the LHC has actually mapped out the space for excluding, unfortunately, until now, where we would expect supersymmetry. So this is a sort of a graph which summarizes in a particular aspect the sensitivity of the result from such a search. What you get here is on two scales, which are the M1/2 and M0 scale, which are the universal gaugino Mascot scales and the universal scale Mascot scales, so at some scale 10 to the 15 GeV or so, this is where all the gauginos of the scalar massive particles have the same mass in this very constrained type of models. And then for given other parameters of the model, like for example tangent beta, which is the vacuum expectation ratio for the two Higgs doublet, and some trilinear couplings, you can map out where the below which the region which you exclude for superparticles to exist within certain constraints. And in that, within this constraint and within that constraint model, you see also that you have the ISO gluon lines here and ISO squark lines. This is 750 GeV, 1 TeV. So at some regions you start to probe within this constraint model masses up to a TeV not seen. In fact, the colors is what we knew before from Tevatron experiments, also from lab. They were sitting here, so in 1 year you sweep out from this now small spot, as one sees it, around 100 GeV or so, to some of these masses of 500 GeV and up to tails in an M0 of almost 2 TeV. The rest, the uncertainty bands you see here, is the usual uncertainty which we have when determining such limits. So, I told you there are very many channels, and this is actually a summary of all sorts of channels, in this case for the CMS experiment. The real thing to remember is, if you want to see the big picture, is the sort of the envelope line which you have on top of that here. But these channels by themselves, they don't really come to their value plotting here, because it looks like, yeah, why would you look in multi-leptons if you have already excluded some region with other techniques? They have their value if you look at different type of models where, in fact, multi-leptons could be produced much more easily than multi-jets, for example, and then things can be reversed. But this is for this constrained MSSM model again, what you see. So there's a lot of lines, and so you get in that model up to starting excluding gluons up to a TeV and maybe squarks up to 1.25 TeV. Now this are in fact the light squarks. These are not necessarily partners of the heavy squarks. So a partner's bottom or stop would be different, because the cross sections to produce them are quite different. In fact, this plot looks horrible in a way, so we call it the spaghetti monster plot, but it's somehow the most, I would say, condensed form of showing where we have not found SUSY so far. Another way of showing it is, that's a result from Atlas, and it's probably difficult to see, but this is again for masses of particles involved for so-called simplified approximations, they call simplified models, to the analysis or to the data sets we are having, when you have 0 leptons, 1 leptons, d quarks, and things like that. Then you can find out for your favorite channel what that relates to, in, for example, a minimum mass for a given particle. We do have interesting events. This is not simulation, this is true events. For example, you see here an event with 5 jets and a very large missing transverse energy. This CMS event, for example, has a total transverse energy, which you see going into the detector of about a TeV, and there is a missing ET, it's HT is just calculated only from the jets, not from everything, of about 700 GeV. Typically, this is how such an event would look like, a SUSY event, if it were to be produced. But one event or a few events don't make it. You have to actually see that you have an excess of a background. And there are standard model processes. For example, when we would have a Z produced here, and the Z decays into neutrinos, it would also give this kind of pattern. And here's one of the events also from Atlas. So, what's next with SUSY? I think the first wave, the first tsunami of results which we had to attack SUSY did not give an easy discovery. It could have been that easy, that SUSY was just around the corner, and the most, I would say, brute force method to look at it would actually work, would actually come up. That is not the case, at least not so far, and we will of course continue to look in that way as well, but at the same time we also have a change of paradigm, that we will be looking at more sort of sophisticated type of ways for finding supersymmetry. Going not just to these very constrained models as a guideline, but taking other possible and equally valid models for that matter as a guideline. There are all sorts of workshops set up for that to condense. And there's, I think, sort of a conclusion that is emerging, and that is what we should be looking for, that if for SUSY, for what is really needed for SUSY to do the work and to do what I gave on this transparency before, why it would all be good for you, give a dark matter candidate and so forth, then this would be the minimal configuration of SUSY we would need. We would need to see a Higgs around 120. This is not a precise number. It is, by the way, Nima Kanyamet who gave us at the lecture, and he uses PowerPoint in a special way, so I had to copy this out from his talk. So a Higgs around 120. Maybe that is on its way. We saw that last time. Maybe also not. We'll see. The squarks themselves could be very heavy, maybe 5 TeV or so. They're sitting up somewhere, except for those, and therefore I stressed that a moment ago, which are the brothers of the top and the bottom quark. So the stop and spottom. They should be light because they are the ones which are really driving to do supersymmetry, what we wanted to do, namely to get these cancellations and make sure that we don't have divergences, for example, to have that being explained. And that should be of the order of a few hundred, well, you know, 500, 400 GeV or so. If that's going to be much higher, it's possible, but then we start to introduce some kind of fine-tuning again. Not as dramatic as the one with the standard model alone, but also the fine-tunings of the order of a % or a promille or so. So it will be uncomfortable if these will be pushed too high. And also the gluino itself shouldn't be too much higher than, say, 1.5 TeV. Now here we're about 1 TeV or so already with our exclusion. This one's, we haven't been really very sensitive to those with the analysis which we're doing, because we were not using anything particular to enhance the fact that it could be a third family type of squark which we'll be looking at. A way of doing that, for example, is seeing if there are tops in these complicated decays we are having, or if there are B quarks in there. And so that's next on the list of what we're doing, and there are the first type of analysis going on, for example, the searches for direct spot production, and right now we push limits up to like a 300, 350 GeV or so. And there are other analyses going on too for other types of models. It could be like, you know, we have models where photons play a role, maybe gauge-mediated models, but I will not spend too much time on that. Also, I assume so far that there is this supersymmetry number, which is always kept. And that's not actually God-given. There are SUSY models, they are a bit more sort of involved, but you can construct SUSY models where you do not need to keep so-called RP conservation. So you have RP violation in there. And RP violation would mean that there is no dark matter candidate coming from that side, so that must be something else in that case. What it would lead is that you have not particularly missing ET in the events, and in fact you would be able to construct everything which is around. For example, you produce heavy squarks, they could go, for example, to 3 jets, so you have a 6-jet event, and you can reconstruct back these masses here. Not easy, but being done, also being looked at, and so far we are with gluino masses up to 280 GeV, where we actually didn't see signal yet. SUSY could be also very hidden, and sort of history is repeating itself. Well, I said before that my theory friends were having good fun to tell us for a while what we would not be able to see with our detectors as we constructed them. Now we know what we're able to see, but still, SUSY could be somewhere hidden in a conspiring way, and there are, again, interesting workshops which are being driven by going for things like next to light next stop as the next lightest particle, collective R parity violation, stealth SUSY. I don't want to explain all that, but these would be ways which would make it very difficult for us to see, but possible. Just we need to have a dedicated analysis for that. Okay, so far for SUSY, so we're still on watching out for that, obviously, and that will certainly become a main topic again next year, when we are going to have much more data than this year. Now let's look to extra space dimensions. Extra space dimensions addresses the problem which we are seeing from a different side. Before we had a problem that if the Planck scale is so far and the energy range is so far that, for example, the Higgs would blow up in mass, or the other divergences are going up, and we need this enormous fine-tuning to make that not happen. and say, well, you know, if you can't get to the mountain, maybe you can have the mountain coming to you, and that is basically what these extra space dimensions are doing, or these extra large dimensions. So what are they? They assume, and this is cartoon again, that, for example, and there are different incarnations, I will show that in a second, but take the simplest one, is that, for example, gravity could live in more dimensions than just the 3 dimensions we see around us. Now you can say, where and how could you hide extra dimensions, for example? They could be very small, and they could be curled up in a way that with each point of space that we see, in fact, there are coordinates related to that, like a rotational type of coordinate, so that in a given point you could have actually sort of like an extra space or an extra dimension sitting. And that is sort of the way to visualize that. It's very difficult to visualize it in a picture. This is the 3D brain which we are living in, and this is gravity, which can move on to that. Now that is expected to happen only at very small distances. Small, but they could be even of the order of a millimeter according to initial, or fraction of a millimeter to initial estimates. Probably that's by now ruled out, but it could break open as you increase the energy, that suddenly this extra space opens for you, or in this case for gravity, and gravity would be the only guy in this particular model who could go into that. Now what would happen then is the following. This is gravity as it grows with energy, and these are the other 3 couplings contracted, and somewhere at the Planck scale the electromagnetic force and gravity gets about the same size, 10 to the 19 GeV, far away from us. However, if gravity on its way here suddenly has an extra dimension to which it can expand, it would grow much, much faster in strength, and in fact the real point for the Planck scale is actually here, much, much closer to us. And this is just a mirage from the fact that we only look here and we extrapolate from there. We haven't seen that dynamics yet. Hence, the Planck scale would come much, much closer to us, maybe even in the TeV range. That's the idea of these extra dimensions. Now, there are lots of them. The one I described is sort of the so-called ADD one, the Arcanghamid and Bimopoulos-Valley type of one, which was brought at the end of the 90s to us, and that essentially assumes that gravity is the only guy which is going to expand in the extra dimensions. There are others. There's the warped extra dimensions, the Randall-Sundrum ones or RS ones, which are actually of a different nature. They assume 2 brains, on one of which gravity is living and one of which we are living, and the space is very warped in between, so that you have a very strong gravity living on that brain. It's very weak by the time it reaches our brain. The reason why that's interesting is because that has quite different phenomenological consequences, for example, if we are start to hit that, and it would actually create heavy resonances, which we should be seeing. Then there is even a third one, which is very democratic, which allows everybody, not just gravity, to go into the extra dimensions once a certain energy is reached, or once a certain small dimension is being reached. And that, again, is something special, but that looks very close to, in fact, to supersymmetry, to create a partner, and even multiple partners for every particle we know. So the U quark will have different U quarks in these so-called ED space that's coming as a higher mass particles. So these are a few experimental measurements where we're looking for them, these extra dimensions. If these ADDs exist, we expect that the whole tower of gravitons can actually couple to standard model processes, such that the net result is that the cross-section to produce, for example, in proton-proton fusion, a gluon going in this way, and a graviton balancing that is substantial, is measurable. And the size of that cross-section depends on the new Planck scale, where it is. If it's 1 TeV or 10 TeV makes a difference, and how many, in fact, extra dimensions we have. Because it's not said that it's just 1. It could be 2, 3, 5. So, by analyzing that, and then within the context of an analysis in terms of the scale or the extra dimensions, we can see to what level we can test the scale. What we would see is that if we look to the missing ET of selected events which have one gluon and nothing else on the other side, so basically one jet coming out here. In other words, monojet events. Counting them and seeing the missing ET distribution, we would expect something like that to set on compared to the colored histogram here, which is the background here. So as it looks, the data, the black points, are quite in agreement still as it is with the background estimate, which comes from data evaluations itself. And then again, yet no signal for these kind of phenomena yet. Limits which we are setting, Planck scales have to be over typically between 2 and 4 TeV or higher in order to be compatible with the data. So for higher, we don't have a sensitivity yet, then come with more data. But you see these events, for example, this is a monojet event. The only thing you see of course the underlying event, which means some soft tracks which have nothing to do with the Hall scattering. But if you put a bit of a PT threshold on this Lego diagram, you see the jet sticking out, which is this jet here, which is 600 GeV, and there is nothing else in the detector that balances that. So that is how such a signature would look like. But again, for example, if that jet is balanced against a Z boson, and the Z boson decays into 2 neutrinos, that would give exactly the same signature. So one event you cannot make a thing. Yes?
In this experiment, what is the evidence for the number of extra dimensions?
I'm telling you about it. Listen.
So, I listened, but I couldn't understand.
So at the moment we have no evidence because then the data should lie on this plot here for the one I just discussed. But it doesn't. It actually follows the background data which is dominated by the process which probably this event is which I showed you before, unless of course it's a real event with the graviton emitted, but it's probably an event where you have a jet and a Z boson, and the Z boson goes into neutrinos. So you have an unbalance in your event, because on the other side of the event, which are taking the transverse momentum away, it's probably neutrinos which are running with that. And that's the background we find. And this is the background as it gives, and so far we find we are consistent with the background. So it means that if these things sit up, they will have to sit up at higher masses here, but not here. And that's how we continue to look for that. And this is what the Randall-Sundrum wants. You expect a resonance to build up, for example, in a diphoton spectrum. So these are two photons, you make the invariant mass, that's what plotted here. Again, this is the background, the colored histograms. This would be a signal, this is the data. And again, you don't actually see your data jumping up here or there or somewhere to give that present yet. So again, we put limits at the moment up to Planck scales again of 2 TeV or so.
Sorry?
Yes?
Are these blue lines the error bars in the future here?
Which blue lines? Yes, these are error bars because this is a single event. So the statistical error is 100% here. These are, see, the event count is 1. These are single events. So they have the full error. These are 2 events, 3 events. Yeah, it's logarithmic plot. That's one. Yeah, that's correct. Now, if you have extra dimensions, which we haven't seen yet, but still, if you would have these, you would have a possibility of creating micro black holes, in principle. It's not sufficient to have extra dimensions, but it's necessary. Now you say, if you don't have extra dimensions, why would you even bother to look at micro black holes right now? The reason being that actually the fact that you have extra dimensions could be seen easiest in some cases through the study of the small black holes. Now first of all, the small black holes, this is always a name which people get a bit scared about, but one shouldn't be, because these black holes are unstable, and we can discuss if you want why we know even experimentally, if they were to exist, they are unstable. We wouldn't be here sitting to talk about it, by the way, if they were not, because we would be bombarded by high energy particles which would create black holes in our atmosphere, in our Earth. Anyway, so they are very safe. They decay 10 to the minus 27 seconds, so don't be afraid. But if they decay, they look spectacular. This is a simulation. That's an event of a black hole which radiates off within that time all its energy that it has, the 5 TeV or something that it may have acquired during the collision, and you see that splashing all over the place in a more or less spherical way. That is a characteristic of doing these things. If we were to see that, that would be very spectacular, because then we actually open the perspective of studying quantum gravity in the lab, which is a dream of I know, many theorists. So this is what would happen. The fact is that if the extra dimensions are there, the Planck scale is close to us, which in itself increases the so-called Schwarzschild radius. The Schwarzschild radius is the horizon in between. If you bring two components, they will actually cluster and make a black hole. So two quarks could come in what is now a very, very big Schwarzschild radius. If the Planck scale is 10 to the 19 GeV, then that is enormously small, and would actually never happen that you would keep, well, you can never say never in quantum mechanics, but in any case it would not happen in any way that we would notice it in the experiments. But if the Schwarzschild radius is large, because the Planck scale is in the few TeV range, this could happen, and then you would have something out of there evaporating in this short time which we are having. So what we look for lots of energy in the detector, scalar sum of energy to be very large, and we try to understand in the multi-TeV range the events with a lot of scalar energy. QCD events, strong interaction jet production, also can produce events with sometimes many jets and a lot of energy in there, and that is the background we have to find. And you see, this is how it would look like. So again, this line here is an estimate from data itself how this variable, the total energy, the scalar sum of all the transverse energy, in fact, is looking like in the detector as function of processes which we know, which are standard model processes. This would be the shape you would expect if indeed you would start to see the onset of production of such guys here. There is big uncertainty, by the way, in these cross-sections, but nevertheless, this is sort of a shape like it would look like. And as you see, alas, again, things lie very close to what we expect the background will be doing. So at this point in time, we would say that up to 5 TeV or so, for particular category of cross-sections, we are not seeing this kind of black holes to be formed. But again, we have very nice events like that. You see, this is an event, very, very spherical, a bit like the simulation I showed before of a black hole. But it has 10 jets even in this event, which is quite energetic and a total energy of like 3 TeV or so. But again, standard model processes can give you such events with a given rate. We have to find the excess above that. So here you see a couple of people quite interested in doing these studies of these black holes in front of our detector while it was still under construction. And I told you, searching for black holes is safe because they evaporate immediately, but you can't be safe enough, so we also asked them to wear helmets just in case. There are many other searches. New gauge bosons, cold resonances, objects decaying into top quarks, strong electric symmetry breaking, fourth generation of quarks, subtraction, technicolor, long-lived particle, dark sectors, more, and so forth. We look basically for all of that. And if you would have found it, you would have read it in the New York Times or Pravda or well, whatever it would come. Since you didn't read it, I can talk now another 2 hours on limits we are setting, so I'm not going to do that. I'm going to just show a few examples of what we are doing. It must be smaller than 5 times 10 to the minus 18 centimeter. And quarks remain the elementary particles after these first results. There is not what is sometimes called a prion, a particle sitting in the quark that you can see. If it is there, it's smaller than that. Maybe we see it in the future, maybe also not. Fourth generation, I will skip. We also look for new, like bees and tops, and but they are not there. And there are a few more examples in the talk, which I will not go with. You can look at leisure when it's on the web. This is again small for you to see, but not meant with Monte Carlo so far, to see if there is something which is deviating from that. In an automatic procedure, I mean, these are 60,000 histograms. We don't have probably enough students to look at all of them, so we have a computer looking at them, and it would find, for example, if there is a deviation of that sort, and then an alarm will go off, and then we have to start thinking. It's not that, you know, immediately we push a button and the paper comes out. We actually have to think what that means. So far, all these alarms meant that, you know, there was something missing in the Monte Carlo or something to be called up in this simulation. But we have a watchdog out there, for those classes we don't even look at. This is the summary so far of what the reach is of the outgoing of the searches for the standard model, for DB on the standard model. And it's very simple. You only have to know 3 numbers. And they're simple numbers. They are 1, 2, 3. So it could be more simple. It will never be as simple again. For SUSY, we are typically probing up to 1 TeV now. That's our limit where we are sitting and getting the results. For gauge bosons, like Z primes, W primes, and so forth, 2 TeV. And for the ones we can most abundantly produce, like in jet interactions, like for example excited quark, colored objects, it's about 3 TeV. This is where we are now with the searcher. So any new physics has to be more massive than that, looking at these 3 categories here. So let me spend like 5 minutes or so on some weird signatures. Some things for which we actually did not build the detectors, which actually weren't even talked about in most cases by the time we built these detectors, but which were sort of, as I invented, as a bit of a blood sport to tell us you may not see this. And that's again this charge which I said before with this, and the same thing, the same story here. But let's look at a few. For example, long-lived particles. All what I said before now assumes that the particles, or whatever we have, either escape detection, like a graviton or like a neutralino, or the others which we produce, they decay into particles we know. A Z prime decays, for example, in an electron and positron, or muon and antimuon, or the SUSY particles decay into jets, leptons, and one particle which escapes. So everything decays in here. So very well, recently, this last 5 years already or so, more and more models or ideas came up where particles are going to be produced, massive particles, few hundred GeV, and they are actually not decaying. They will live for a while, long enough at least for traversing the detector. So if they live a second, that's already enough, because in something like 100 nanoseconds they're out of the detector. And there are a whole class and zoo again of such objects which came alive. For example, an interesting one is an R-hadron. This is in fact assuming that you're in a supersymmetry situation where the quarks are enormously high mass, maybe 10 to the 10 GeV, so 10 to the power 10 GeV, very, very far away. In that case, a gluon will be having a very difficult time to get sort of back to a normal state, or gluino at least, and it will live for some time, maybe seconds, maybe a week, could be a month. When it's produced, since it's colored, it has to dress itself up like any decent colored particle before it comes out to look color neutral. So for example, it grabs a gluon in the neighborhood and it comes out and can as such form an R-hadron. And they are very funny, these particles, because they will move very slowly to the detector. They will not behave neither as a muon, neither as a hadron, but something in between. They will lose some energy in this thing, and they even may have very strange properties that they could change charge on the way. If it, for example, is going with a quark together, it can have, or a quark pair together, it can have charge, and then due to the collisions, it can change its charge on the way through. This is a headache for reconstruction programs, to have a particle you have to track which can actually change charge. This is not foreseen. They will lose energy because they are very massive, and they can get stuck. They can get stuck, and John Ellis and I thought they might get stuck in the cavern wall here, and that would be an interesting thing to actually try to get them out of the cavern wall, but I won't go into that. You may ask John in the next lecture if he starts to discuss this. But more reasonably, in fact, they can get stuck in the detector itself and sit there. They sit there maybe for a couple of days. And then they decay. A flash of energy you're going to have in your detector, which has nothing to do with the bunch crossing. This particle was produced a week ago. The beam may not be even on. In fact, the beam should not be on in order to see them. And you have to keep the detector active, looking for things also when there is no beam. And then see if you get some flash in your detector here from one of these particles, these strange particles which were stuck in there. So originally they told us you can't measure this, but we changed our triggers so that we can actually stay active also when there is no beam in the machine, and that's particularly a good moment to search for these. What are the chances to find these? Well, probably not very high, but we have the duty to look at that, and we looked at that in the different trains and saw some events happening, but they were completely consistent, for example, with cosmic rays which come into the experiment, which is not too much, in fact, with the energies, because we had good CAD design, but we had a handful of these events, but just as much as we would expect from the background. So again, we put limits on guys like that. And they're now up to 600 GeV or so. And there are more. You can also look at the time of flight, because this guy will go actually slower than speed of light, certainly not faster. And also the energy it loses on the way is important, but I will not go back to that. And there are lots of other actually objects which we haven't even yet looked at. So if there are ambitious students in here, you want really to go for something new which isn't particularly covered yet in the experiments. I mentioned just fractional charge type of objects, monopoles, narrow resonances, quirks, hidden valleys. You don't want to know what that, well, that's a quirk, but I'm not going to give the detail, just if there's a question on that. So, lots of opportunities for PhDs, and certainly opportunity for one of you to make a major discovery if you choose the right topic. Okay, I'll finish since my time is up. I just finished by saying what's the LHC going to do next. And this is hot off the press if you want. This is from last Friday, oh, it's now a week ago, Friday, in Chamonix, when the machine has a retreat and they do some skiing and they also have some talks, and they decide how they're going to run for the rest of the year. And the decision is, as we heard already a few times, the beam energy is going to go a bit up, so 4 TeV, 8 TeV center of mass energy in total. The squeezing of the beam is going to go down, I mean up, the squeeze is going to go up, so the beam parameter is going to go down. If you go to 60 centimeter, you get more luminosity, you get 1/3 more luminosity than if you go 90 centimeter. And here you see this thing's going. The 70 is sort of the baseline, but I think 60 is possible. And that would mean that we have, by the end of the year, this is the year running, something going up, some stops and so forth, something like almost, this is almost 18 inverse femtobond being added to the 4 or 5 which we have already. So 20 in total is certainly not out of range here. And already the press picked up on that. This is from a few days ago, that they say the LHC energy boost will aid hunt for the Higgs boson. So if you were doubting what I'm going to say, you can believe the BBC here. They're usually right. And this is over many years what's going to happen. This is this part. We still say it's total of 17. We think now this is more. This is slightly older here. There will be then a long shutdown for almost 2 years, for the years 2013 up to almost the end of 2014. Increase of energy, and this is a logarithmic scale in the luminosity integration which you see here, going up quite strongly there, another shutdown, and then another with 2 scenarios which haven't been decided yet which one they're going to take. But something like 1,000 inverse femtobond or 500 inverse femtobond by 2020 is not out of range. So that is like a factor 200 more than what we have now. Okay, concluding. So the LHC has entered new territory. The ATLAS and CMS experiments are ready for searches for new physics, as you saw. They are ongoing. The most popular example is SUSY, but there are many others searches which are covered, and I covered them only briefly. Some, if you look back to it, you will see there are many models being discussed actually, and results given on that. So far, alas, no sign of new physics yet. In the first inverse femtobond, the first 2 inverse femtobonds at 7 TeV. Stay tuned for the conferences in a couple of weeks, because then we will release the full 4.5 inverse femtobond, and we'll see what that gives. And then, of course, there is a whole year coming. We start already to cut in this what we called, or thought of as were the preferred SUSY regions, preferred from the point of view. There's where we would have liked SUSY to show up, because that would have been easy to go. But it looks like we have to be a bit more sophisticated in the analysis, and we have to dig deeper. There are many opportunities here for young people and new ideas. I mean, in the last years, we We saw really young people coming up with a fresh look at these things, which was very helpful, and we have developed new techniques and new things together with the people with the experience and the younger people. It makes good teams. And some analyses are in fact still with very poor luminosity, but they will be upgraded as well. So in fact the LHC, as far as we experimenters are concerned, did the first grade, not only first half, but the first year, our first real production year this year. And we expect now something that of the order of 20 Verts femtobarns by the end of 2012, and also higher energy for ATV, which will certainly help with the searches. Particularly in the high mass, this 1G, 1 TeV extra is already very interesting. And who knows, maybe soon we will see something. Yeah, here it is. We will see something to celebrate on that. All right, thank you.
Okay, questions?
So now you're saying about the preferred SUSI region, and what is naive or upper limit for this region?
Upper limit for SUSI?
Yeah, so maybe 5 to...
I would say that if we come like 2 to 3 TeV and we haven't seen anything yet, then I would think, to put it in Richard's type of terminology, that field of supersymmetry will actually, a lot of people will leave that and have to think of other solutions. Particularly if we do not see this light stop and bottom. If that's not there, and they are pushed to maybe very high masses, over a TeV or more, then supersymmetry may still be there, but it's not going to be there for the reason we need it. We needed it to stabilize things. We needed it to have to get rid of this big fine-tuning, and it's creating a new fine-tuning. So people will start thinking different directions more. There will be always diehards, which will, never change. But I think people will start looking at other directions there, as there are already many people looking now. But there will be even more people going with it. So I would say 3 TeV-ish for this. Anything at all, and certainly when this bottom and stop are going to be not found below a TeV, it's going to be hard for SUSI to keep its popularity.
As far as I understood, we can find some traces, SUSI particles, by means of transverse momentum laws. But how can we prove the existence of these particles if we cannot detect them?
Mm-hmm. So you actually don't need to prove that that's a particle, because what you're going to do then is, in the decay chain, you will have many sparticles being produced, as I showed. It's only the last one which escapes. And that's a little annoying, because that gives you don't have a closed system to study everything. But there are techniques by looking in the decay chain and reconstructing it, you can actually have information on these particles which were produced in that chain. For example, a squark or a gaugino, which is heavier than the lightest one. And with tricks which you can do on the kinematics, you can even measure properties of these and prove, for example, that they have the right spin, which is the crucial point for supersymmetry, because the partners of the quarks have to have spin 0. The partners of the Z boson, the W boson, have to have spin 1/2. So yes, what we first would see is we would see an excess. At that point, we can't be sure it's supersymmetry, but such that we see something. But then, and that's why we need more data then, but then with more of these events and studying the structure of the decays in these events, we can determine parameters of these particles which are produced.
So you mean we can see, as you said, long lifetime particles?
So SUSI, if I talk about SUSI, I mean the short lifetimes. I mean the ones which decay immediately, and you see only the decay products in the detector. If you see a long lifetime particle, that's a very different story, because then you can do more measurements. Then you can actually see the particle, you can measure its mass directly, for example, from the way it's bent in the magnetic field, from the energy it loses on the things. If there were long-lived particles, actually that would be very spectacular and very useful, because we can measure things much more easily then. But the thing I was talking about is the most difficult one, when everything decays at the vertex and you have to reconstruct the chain from the totality of particles you see in your detector.
Okay, does LHC have something to say about precision electronic measurements, or because it is a quantum machine, doesn't there is any possibility of obtaining better bounds?
Yeah. So certainly, for example, on electroweak parameters, well, there is a top quark mass, which is one of the things we will push, and probably we'll still, I don't know how far we're going to push beyond what the Tevatron is doing. There are plans for measuring the W mass to half of what it is known now, so it's a factor of 2 you can gain here. And particularly you have also measurements on triple gauge couplings and others, so multi-boson production. And in fact, we are very complementary there to an E plus E minus machine because of some of these parameters in the way of testing these couplings are very energy dependent, and other ones are more dependent on precision. So the combination of that is actually working very good. And we are now having, I think also in the next months, some results coming out on that. So yes, a hadron collider is traditionally not known as or not recognized, I would say, as easily as a machine for doing precision physics. It will never be as good as a precision E plus E minus machine, but it will be better than what we know already on some of these parameters. So we will improve electroweak precision measurements as well. Because also there, deviations you may find if you combine the top mass with the W mass and you see where you are in parameter space, and you know, it doesn't match with other measurements you make. It's a way of testing the standard model and finding cracks in it.
Sorry, and it's not quite clear, but as long as the main criteria for both extra dimension and supersymmetry particles is the large missing transverse energy, how are you going to distinguish those events? Okay,
so if you have, it's true, and it's actually always, there's always somebody who observes that, because that's also why I bring it and check who is actually made. You saw that in both cases they use missing transverse energy. So there's a very big difference. In the SUSY type of model, you have a lot of stuff being produced. It was a cascade which I showed, which was very complicated. While here it is just one jet and one graviton. And in fact there is a sister process, one photon, one graviton. So the process is much more simpler for these extra dimensions. Now you do have also in supersymmetry cases where occasionally you can have a very simple decay. For example, a squark is produced and it decays into a quark and this latest neutralino. Then it would look exactly the same. The difference then again is this, what escapes on the side for the missing ET is a spin 1/2 particle. This is a gaugino, so it's a brother or sister of the photon, for example. While in the extra dimension it's a graviton, it's a spin 2 particle. And then again, if you can do at angular correlations or angular distributions, how this jet, as it is produced, is actually angularly behaving, it will be different in an extra dimension model compared to a supersymmetry model, due to the different spin of the particles involved.
Any other questions?
Yes.
You showed this exclusion part for SUSY, and at the moment the hadronic exclusion is the best for missing TV jets. And all the other channels, are they important because the hadronic channel can miss something, or is it important when the luminosity is increasing that they will be more important, the multi-vector than the hadronic channel?
Okay, so they test different things in the model. For example, we produce most likely is gluinos, which go into squarks, and they go into jets and missing ET. So maybe 2 jets on each side of missing ET. This is in that particular model, this constrained type of model, the most favorable way of producing SUSY particles. But there are other ways of producing SUSY particles. For example, you can have a Drell-Yan production of 2 gauginos, so just 2 brothers of the Z boson coming out there, if you want. And they will decay mostly in leptons. Now that cross-section in this particular model is not very large. So the search, when you use leptons, multi-leptons for example, is not going to exclude so much because it's fighting against a small cross-section which you're having. But in other models, that cross-section is much larger, for example, compared to the one which I said before. So the relative proportions of these things can change. So what I showed is only valid within the context of this simple model. But in many other models, in some models you could even not have this main channel which I talked about, which is this jets plus missing ET, or very, very few events. And then the others are becoming important. So each of them will remain important. It just looks a bit poor on that plot. But in the context of our general interpretation for supersymmetry, they are very important. And as said, in some models they may be even dominant over the jet plus missing ET.
Okay, so very short question.
If really there is gravity in this manner, what kind of coupling can correlate the gravitons and the other particles in the Lagrangian experiment?
Graviton, I mean, you're mixing a few things. Supersymmetry and the graviton, I actually never mixed these things. So gravity was not connected with supersymmetry. Yeah, so the coupling is very small still. But the thing is, with such extra dimension models, is that you don't couple to a single particle per se, but you have a whole tower of particles. And for example, in the ADD model, there is a tower of particles going from almost mass equals 0 to infinite, with a spacing of a few electron volts, for example. So you have an enormous amount of particles which are coupling. And the total probability you calculate in this cross-section is the sum of all those. So it's millions of diagrams, if you want, which you integrate over. So the coupling by itself remains strong, remains low per particle, but the phase space to the amount of particles can couple, that is what is increasing, and that is what is being given by these extra dimensions. So therefore, it appears that you can have cross-sections which are becoming measurable, like I showed in this plot, this deviation you saw when you shouldn't be seeing it. But it's because you have a whole tower actually coupling, not just a single particle. That's the picture which is behind it.
Okay, I think if someone still have questions to the Professor Roeck, he can ask it in private discussion after the lecture. And yet we have, sorry.